So the channel allocation is the concept of how to access the common medium. Meaning the common is I'm sharing medium. Like when I'm talking to you over the Zoom, I'm sharing a one mic. And if everyone starts to talk, the Zoom voice line will be busy. Then we are not able to decode, meaning we are not able to understand, right? Like we are communicating over the classroom. So we are sharing air. So one medium is air. So we have to share the common medium. When I talk, you have to be silent, okay? Then how can you make decision who are gonna talk next? That is all about today. So attribute of the channel allocation problem is dynamic or static. Dynamic is everybody is like not busy and start talking. When they start talking, everybody's silent, okay? So opportunistic manner. Static manner is after I talk to, then the clockwise, you talk, then you talk, and sequentially. That's a static. A single channel is available. That is our assumption. In reality, we have a multiple channel, but we are assuming the simpler problem. Then we solve it. Then that problem solved, then the solution can be applied to the more complex one. Is the time is continuous or slotted? We're going to talk about what is continuous or slotted. And carrier sense. Carrier sense is before I talk, I sense, meaning with your ear. When everybody is not talking, then I can talk. Okay. Collision detection is while I'm talking, someone else is also talking. Then I realize my speak is collision. You may say, you go ahead, you go ahead. Okay, I'm gonna talk first. Something like this. Okay. So there is a multiple access protocol. And there is many multiple access protocol, but they are all from this concept. First, Aloha. Aloha is from University of Hawaii. And we have two concepts of pure Aloha and slotted Aloha. Then we're going to talk about CSMA, carrier sent multiple access, meaning everybody sends the channel before they talk. Okay. In collision resolution algorithm, meaning what you going to do? What happened? What you going to do if the collision is unavoidable? Okay. If the collision is estimatable, what you going to do? Can you solve it? Okay. Then we're going to talk about this. So let me connect to my iPad. Okay. All right, so can you see my iPad? Let me also check about the
yes.
Latency. Hello, right? Almost real time. Do you feel the lagging? Hello? No, not at all, isn't it?
No, we don't.
Okay, excellent. So pure Aloha. What's the pure Aloha? Aloha is to say hi without sensing everything over the continuous time. Meaning, when I want to say hi, Aloha, right? So I have 1, 2, 3, 4, 5 competitors in a single channel. Then how many communication was successful? Can you count it? I think this is successful. This is no because of this guy. This is no because of that guy. No, 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 there is some overlap in here, so no. Okay, this is good. This is good. This is good. This is, I don't know. I don't know. Do you see how I cross out? Whenever there is a multiple guys try to talk to in a given channel, it is collision. So to make your communication successful, you should be the only one who talk on the channel. Clear? Okay, let's move on. Say, assumption of the pure aloha is as follows. So new arrival packets at each host are transmitted immediately, meaning if there's something packet I have to deliver, I just transmit it immediately. Okay, there is no delay. If I have package, I just transmit it. Okay, so arrivals are Poisson with the total rate of lambda. Okay, we're going to talk about detail about it. Do you understand the Poisson distribution, right? I believe so. Who's not clear about the Poisson distribution? Is it maybe the different pronunciation, but Poisson distribution, but not as it is not completely Poisson distribution. It's not, but the Poisson or Poisson distribution. When I learned it, I learned as a Poisson distribution. Did you learn in the very basic AMS or very basic computer science math, right? No? No response today? Okay. So, yeah, okay, AMS is 310 or maybe earlier, right? Don't worry, I'm gonna cover what is Poisson distribution, okay? So if the packet is involved in a collision, it is retransmitted after a random period of time. This is called a backlog, meaning if I say hello, then if it has failed, what do? I don't keep saying hello, hello, hello. Rather than doing this, I do backlog, meaning I'm keep silent, stay silent for a while, for a random time. Then I try to say again, hello. Okay, so receiver provides feedback on a received packet to implement the collision detection, meaning if the hello communication, if the aloha communication was clear, then receiver have to provide the feedback, meaning, oh, your hello was well recognized. Then what do? Then aloha again. Aloha, then aloha, okay? So the concept of this pure aloha is no buffering. No buffering meaning a backlog node does not buffer any arriving packet. So if I have a packet to deliver, then I say something, right, to process it, to digest it. While I have something to digest, I don't receive new packet from the upper layer, okay? Meaning there is no buffering. I have no ability to buffer, okay? Or the set of nodes accessing media is infinite. So after 7 transmission, I give up. That is the Wi-Fi rules. But in a pure aloha, there is no give up mechanism. Okay, it's keep trying until you succeed. Okay, let's go on. So what is the Poisson distribution? What's the correct, maybe how you pronounce this? Anyone? Go back?
I think our professor was saying Poisson distribution, but I'm not
Poisson
sure.
distribution? Okay. How about anyone else? No? Nobody? So I learned from multiple lectures, but I prefer to use a Poisson distribution, but Poisson distribution. Yeah. Okay, but if you have a different pronunciation, that is fine. I think it is not from English. That is why everyone else has different pronunciation. People from Russia speak differently. People from Europe maybe speak differently. Okay, so suppose that we can expect some independent event to occur the lambda time over a specific time interval. The probability exact X occurrence equal to, as of this, Poisson distribution. Do you understand? So suppose that we can expect some independent event to occur lambda times over a specific time interval. Okay, so try remember this. And so let's solve this problem. So suppose you work in a McDonald's, okay, as a part-time. So suppose a fast food restaurant can expect 2 customers every 3 minutes on average. So we can understand, oh, we can calculate what's on average. How many customers do you visit in a given time? Okay, I usually have 2 customers every 3 minutes. That's average. Ah, okay, remember this. So what is probability that 4 or fewer patrons will enter the restaurant in a 9-minute period? Do you understand? Okay, so I think everybody is kind of not out of the bedroom. So let's solve this as a quick. Let's solve this as a quick quiz. So if you can solve it, okay, try to solve it. If not, think about it. Okay, so let's talk about for 2 minutes and try to solve this. So suppose you learn in the Poisson distribution, maybe your high school mathematics is enough to solve this. Suppose you have 2 customers every 3 minutes on average, and what's the probability 4 or fewer patrons will enter the restaurant in a 9-minute period? Okay. Okay, let's talk about, let's solve it for 2 minutes. So I'm working at the fast food restaurant. So my average customer is 2 customers for 3 minutes. So what's the probability that 4 or fewer people will enter the restaurant in a 9 minutes? Meaning this, if I convert 3 minutes to 9 minutes, then it will be 6 is my expectation. So you are expecting 6 customers in a 9 minutes. Therefore, your lambda is a 6. So question says, what's the probability 4 or fewer patrons will enter? Meaning, probability the number of customers exactly 0, 1, 2, 3, 4. Sum that up. Meaning, that's your expectation. That's your probability. So we have probability equation. Then from now it is mechanical. So you apply. What's the 0 in a 6? 1, 6, 2, 6, 3, 6, 4, 6, right? We understand what it is. So number of customers is 4, probability of the 4 people coming in my 6 lambda environment. Then you apply to this equation, then you solve it, then it turns out 28%. So if you're working at the restaurant, let's say you're McDonald's, some customer may ask you, oh, what's on average people you come to the coming to the fast food, the McDonald's? It depends on your time period. Okay, how about every 10 minutes? Based on my 10 minutes, you can solve this Poisson distribution. You can explain based on by assuming Poisson distribution, my expected number of the so the expected number of the customer is 28%. How do you solve that? Then you can show that your equation, then your customer will be very satisfied, your mathematical ability. Okay. So David says, that, can lambda be a decimal? Decimal means 1, 2, 3, 4, 5, 6, right? So in a more, So example, so David says, for example, what is if the question asks 4 or fewer people in a 2 minute? Then, so your lambda is, your lambda in this case is 6, right? So you have to convert 3 minutes to 2 minutes. Then you are meaning, then it will be like 1.6, right? Then lambda doesn't need to be decimal. So it could be floating point, then you can keep continuing. Okay, the average won't be like a decimal at every time. So if the question says every 2 minutes, oh, I only know the 3 minutes, then you are converting to 3 minutes to 2 minutes, meaning with the same scale, you have to make your average in a floating point. Okay, so David, is this satisfied your question? Okay, all right. So lambda doesn't need to be decimal every time. Okay, all right. So collision occurrence. Let's go back to the point of the network. So now we understand what is a Poisson distribution. So packets arrival, Poisson with the lambda g. So Poisson with the lambda g is bigger than lambda packets per t. So what's the g meaning? G refers to the mean used in the Poisson distribution over transmission attempt amount. Okay, so attempt. Okay, that is on average the G transmission attempts per frame. So in a given ALHOA, what is the vulnerable time? So let's solve this. Say, I want to transmit this package. Length of t. What's my vulnerable time? Meaning, if someone else start to talk before me, okay? Anybody who started in here, that is fine. But anyone who started earlier than me and overlaps my package, that's vulnerable. I am vulnerable at that time, right? Meaning, then, if someone else has tried to talk before I finished, that is my vulnerable time. If someone started talking in here, it is fine, but before I finish, it is vulnerable time. So what's my vulnerable time in this? So
1t ahead and 1t fourth.
Okay, thank you. So let's solve this. So in the view of the t, where's my vulnerable time start? My vulnerable started in here, not here. Why? So I'm talking about my packet, my messages. So my vulnerable time starts when I start to talk. Clear? If someone else was there before, then if I start, so I am also vulnerable. So my starting in here, then when does it end? So if someone else let's say all the packet length is same. If someone else start to talking before I am close, I'm finished to talk. So someone started talking in here, make me vulnerable. But someone who started talking right after my talking is not vulnerable, right? Therefore, my vulnerable time is 2t. Clear? Let me explain one more time. So, I am talking at the T1. I am talking at the T1. Then if I am the only one, I am successful communication. If I am start to talk T2, if someone else is trying to talk at T3, I am collision. So I transmit again. If nobody else was there, I am clear. At T5, I am clear. Okay. So my transmission starting at T, if someone else was before me, then I am vulnerable. Okay. If someone else start to talk right before my end, then I am vulnerable. Right. Therefore, so let's say this is my packet. Then when does it start? I'm start to vulnerable from here to here. Right. Because I have to start communicate, then I am vulnerable. If I don't start, then I'm not vulnerable. Okay. If someone else was here before me and I started, meaning I'm vulnerable. Okay. Someone else started after me, but they overlap with me. Some section of overlap, I am vulnerable. Therefore, vulnerable period is if just starting as my point, then for t, I am vulnerable, of course. Okay, I have to extend this time to t, then I am vulnerable. Why not 3t? Because you have to start. Before you start, you are not vulnerable. Therefore, you have to count from here, this point, then up to here. Then your vulnerable time is 2t. Clear? Okay. So some equations are this type. Let me go back to